Here's what you're about to find out. Why a nuclear plant can never explode like a bomb. What that eerie blue glow inside the reactor really is. How engineers plan to store waste for 100,000 years. Why Chernobyl's reactor design was so uniquely catastrophic. Right now, somewhere in France, a single fuel pellet the size of a pencil eraser is producing as much energy as 800 kilograms of coal. And it will keep doing that for 4 years straight. Inside a nuclear power plant, the physics happening every second would have looked like magic a century ago. So what is actually going on in there? Not the politics, not the disasters, just the machine itself. How does splitting an atom boil water? And how does that water keep the lights on for an entire city? Most people have a rough idea that nuclear plants involve radiation and steam, but the mental image usually stops there. A vague sense of green glowing rods, mysterious pipes, danger signs. The reality is far more precise and honestly more interesting. At its core, a nuclear plant is an extraordinarily sophisticated kettle. The nuclear part is just the heat source. Everything downstream, the turbines, generators, and transformers, is engineering that would look familiar in any coal or gas plant. The real difference is what makes the heat. That heat comes from uranium. More specifically, a rare form called uranium-235. Natural uranium ore pulled from mines is mostly uranium-238, which is stable. And uranium-235 makes up less than 1% of what comes out of the ground. To use it as fuel, engineers enrich the material, meaning they separate and concentrate that tiny fraction until it reaches about 3 to 5% uranium-235T. That enriched material then gets pressed into ceramic pellets and loaded into long metal tubes called fuel rods. Each fuel rod is about 4 meters long and roughly as wide as your thumb. Bundle hundreds of them together and you get a fuel assembly. Load roughly 200 fuel assemblies into a steel vessel the size of a small house. Submerge them in water and you have the core of a reactor. That vessel, the reactor pressure vessel, is where the chain reaction happens. The walls are steel, usually around 20 centimeters thick. Around that sits a concrete biological shield. Around that, the containment building, reinforced concrete, sometimes 1.5 meters thick. Now here is something that surprises most people. A nuclear power plant cannot explode like a nuclear bomb. The weapon enrichment is above 90% uranium-235. Reactor fuel sits at 3 to 5%. That concentration cannot sustain the runaway chain reaction a bomb requires. What a reactor can do is overheat if it is not properly managed, which is serious but fundamentally different. The entire engineering history of reactor design is really the story of how to keep that heat under control and what to do if something starts to go wrong. Before we go inside the reactor, it helps to know the one concept that makes all of this possible. Fission. When a neutron, a subatomic particle with no electric charge, strikes the nucleus of a uranium-235 atom at just the right speed. The nucleus splits. It breaks into 2 smaller atoms, releases energy as heat, and throws off 2 or 3 additional neutrons. Those neutrons can then strike other uranium-235, which split and release more neutrons which strike more nuclei. This is a chain reaction sustained controlled. It produces continuous heat. That is the entire engine of nuclear power. The chain reaction inside the reactor does not start by accident. Operators initiate it deliberately and they can slow or stop it just as deliberately. The main tool for this is control rods, long cylinders made from neutron-absorbing materials, boron-hafnium or silver-indium-cadmium alloys. When fully inserted into the core, they soak up neutrons and the chain reaction cannot sustain itself. Pull the rods partially out and neutrons find uranium-235 nuclei instead. The reaction begins. The depth of insertion determines the reactor's power level. Fully out means full power. Fully in means shut down. There is a second layer of control built into the water itself. In most Western reactors, the same water that cools the core also acts as the moderator. A moderator slows down the neutrons released by fission. Fast neutrons are actually less likely to split uranium-235 than slower ones. When water heats up, it becomes less dense and moderates neutrons less effectively. So if the reactor runs too hot, the chain reaction naturally weakens. This is called a negative temperature coefficient, and it means the reactor has a built-in tendency to stabilize itself. Heat up too much, react less. The most common reactor design in the world today is the pressurized water reactor, or PWR. About 70% of all operating reactors are this type. In a pressurized water reactor, water flows through the core at extremely high pressure, roughly 155 times atmospheric pressure. That pressure keeps the water liquid even at 325 degrees Celsius. Boiling it in the reactor itself would create steam bubbles, which would disrupt the moderation. So the primary loop stays liquid. The heat it carries travels to a separate secondary loop where the water there does boil, and that steam drives the turbines. The device that transfers heat between the primary and secondary loops is called the steam generator. It looks like a very large metal cylinder. Some are 20 meters tall and weigh 300 tons. Thousands of thin tubes snake through its interior. Hot pressurized water from the reactor flows inside those tubes. Water from the secondary loop surrounds them on the outside. The heat transfers through the tube walls. The secondary water boils, becomes steam, and heads toward the turbines. The primary water, now cooler, loops back to pick up more heat from the reactor. The two loops never directly mix. That steam, now at high pressure and hundreds of degrees, enters the turbine hall. This is the part of the plant that looks most like conventional power generation. The steam spins a series of turbine blades. First high pressure stages, then lower pressure stages, extracting as much energy as possible from the steam's pressure and heat. The turbine shaft spins a generator. The generator produces electricity. At a large plant, a single reactor might spin a turbine shaft at 1,500 revolutions per minute, generating over 1,000 megawatts of electricity. That is enough for roughly 1 million homes. After the steam passes through the turbines, it still holds too much heat to release directly. It enters a condenser where cooling water drawn from a river, lake, ocean, or cooling tower circuit reduces it back to liquid water. That liquid water then gets pumped back into the steam generator to start the secondary loop again. The cooling towers you see at many plants serve exactly this function. They are not releasing radioactive steam. They are releasing plain water vapor from the non-reactive third cooling circuit. The white plumes are just water. Most people assume they are something more sinister. Now step back and look at the whole system. 3 separate water loops, not directly connected. The first loop is radioactive. It touches the reactor core. It never leaves the sealed primary circuit. The second loop never touches the reactor. It produces the steam that makes electricity. The third loop, just cooling water, never touches radioactive material at all. This separation is intentional. Even if the turbines or generators have a mechanical failure, the radioactive portion of the plant stays isolated. The engineering layers are designed so that no single failure can propagate all the way through. The control room is where the human side of all this physics becomes visible. At any modern plant, operators monitor thousands of individual data points, coolant temperatures, neutron flux levels, pump pressures, valve positions. The panels stretch across the length of a room. The operators work in shifts 24 hours a day, every day of the year. Training takes years. Before anyone touches a control at a real reactor, they spend hundreds of hours in a full-scale simulator, an exact replica, the control room that can recreate any emergency scenario. Licensing exams are written and practical. Pass rates are not high. Inside the containment building, the reactor core sits submerged in water that glows an extraordinary shade of blue. This is called Cherenkov radiation. When charged particles from the fission reactions travel through the water faster than light travels through water, they create a kind of electromagnetic shock wave visible as a blue luminescence. It is one of the few places in industrial technology where you are literally watching quantum physics with the naked eye. Reactor technicians and physicists describe seeing it for the first time as genuinely arresting. The blue is steady, even, and absolutely silent. Those fuel assemblies in the pool are not just sitting there passively. After fuel rods have been used in the reactor for several years, they are considered spent not because they have lost all radioactivity, but because the balance of isotopes has shifted enough that they no longer sustain an efficient chain reaction. Spent fuel is intensely radioactive. It generates heat from the decay of fission products inside it, even without a chain reaction running. Pull it out of the reactor and it still needs active cooling for years. This is why spent fuel pools exist. Large water-filled tanks where assemblies sit and gradually cool. The spent fuel issue is where nuclear power gets genuinely complicated. After roughly 5 years in the pool, assemblies are cooled enough for dry cask storage. Thick steel and concrete containers that use passive air cooling rather than active water systems. They require no pumps, no electricity, no moving parts.